Hi, hi, Raimundo.
Hello, Jelonek. How are you doing?
Well, thank you. Well, and you?
Yeah, I'm doing well, thanks. Everything's okay here. I thought
Okay.
you, I thought you were able to travel to Vitoria.
Yes, yes. Because but in fact, I spent 1 year in Brazil.
Ah,
The next year,
I didn't know.
from August to August.
I see.
Excuse me, could you explain me how to use this my presentation on this platform? Because I have never used this platform.
I see. You are using the Google Meet, right? I
Yes.
think that's okay. See if you can find a button saying share screen or screen sharing. It's
Uh,
supposed to be a button on down on your screen.
I can see sharing. Yes,
Yes, it can be sharing this. Click on that.
but it is only presentation, not more. There are options. There
Yeah,
are options.
yes, there are some options you can choose. You should choose the option to share your screen.
Ah,
After
let
that,
me-
you can show your PDF on your screen, and everyone
mhm.
will
But
be
I
able.
can't see this option. There is option presentation.
Yeah, click on that just to see what happened.
What happened? Okay, what is this here?
The PDF of your presentation is is already open in your screen.
I have to open it. Oh,
Yeah,
you are
open
right.
it. After that, try to share your screen.
Okay, this is open. And now what? Could you see something? Not.
No, not yet.
Okay. And
Oh,
now?
now it's loading. Wait a minute. It is loading. Okay,
Okay.
good. Now I can see your screen and can see your slide. Good.
Okay,
Try
that's
to
okay.
wide the screen. There is a button up, which is able to, rescale your screen. Now it is disappear. What happened? Did you close it?
No.
Just click on the PDF again.
Yes.
Okay, good.
There is?
Now it's okay. I can see
Okay.
your
Okay,
presentation.
that I know what I have to do. Okay.
Okay,
It's
good.
enough to
Okay,
click on the PDF.
okay, good.
And Raimundo, I would like also use some pen because I would like to explain some proofs using pen. It's possible?
It is possible if your PDF or if your device permit it. Do you have what kind of
Um,
pen do you have?
no, some picture to write a picture. Is possible or not?
If your device allow you, it's okay. I mean, I have a special app that allow me to use the pen, a special pen on my screen. If if you have that's
Mm.
okay. Otherwise, you can just show your screen.
Aha, maybe I choose here my okay.
If
Maybe
you want,
I
you can test it. Open your PDF
okay.
again
Maybe
and
some
try to
paint.
write
Okay,
something
okay.
on
I
that
I
just
try.
to see what happens.
Okay, okay. Maybe.
Hi,
But that is. Do
can
you
you see
see?
me? Okay, we are seeing and we are hearing you discussing if your presentation is okay. So we shall have a small
It's
and
okay.
very
Okay,
fast.
okay. Now I can see the blackboard, the
Okay,
whiteboard.
okay.
Right on it.
Something like
Okay, good. I
So
can
you
see
are
that.
in the screen, on
So
the
you
screen.
have to exchange, from one screen to another screen. When you want to make some scratch, you have to exchange the screen. and after
Okay.
come back to the PDF screen.
And now it's okay. Okay, yes.
Yes. Maybe you can
Okay,
put
good.
side by side, but
Okay.
better now just to exchange the screen and make the scratch
Okay.
as one.
Okay. That I know what I have to do. Okay.
Yes. Okay. Good.
So you're going to start at 9 a.m. Is that everything okay with you, Zbigniew?
Yes, probably it's okay.
Okay, so you begin at 9. Before you're going to have
I know. I know.
a fast ceremony in order to direct to say some words, and I will
Okay. Okay. Okay.
make some announcements. Okay, see you.
See you.
Tá fechado, tá ligado. Good morning. We are going to start the 5th Brazil-Chile-Mexico meeting in Singularities and second meeting on Foliations and Singularities. I would like to invite Professor Etereldes, Director of the Center of Science. Exato. Please, Etereldes.
Bom dia a todos. Em nome da direção do centro, quero cumprimentar a todos, dar um bom dia, boas-vindas. Dizer que o Centro de Ciências Exatas hoje está muito orgulhoso de recebê-los aqui. Esse é um movimento de resistência a tudo que a gente vem passando, né? A ciência, a educação no Brasil tem um movimento dessa qualidade no nosso centro. transmitido para aqueles que não puderam vir, não puderam ser financiados pelos cortes que a gente tem recebido, né? Tem passado por muita dificuldade na questão do financiamento da ciência e da educação superior no Brasil, mas ainda assim, um evento dessa natureza, dessa qualidade, depois de 2 anos de pandemia, é um orgulho muito grande a gente receber aqui no Centro de Ciências Exatas. Desejo um excelente evento a vocês e, bom, é isso. Como diretor, estou por aqui para dar o apoio que vocês precisarem.
Thank you. I would like to invite Professor Leonardo Câmara to talk a little bit the committee organized.
Thank you, Caroline. Well, I would like to welcome you all, and here and online. We have some, well, first we'd like to say welcome, as I said, and to say a few words about biosafety and some announcements, some technical announcements of trivial nature, and further how we're going to work with this hybrid system, okay? So first I would like to thank the scientific committee and the organizing committee. I'd like to mention especially those who are here. Carolina Pereiro, could you stand up, please? People know. If you have any kind of question, these people from the organizing committee can help you. Thiago Silva, he's not here, but he'll be soon. And Fernando Reis is over there. Leandro Oliveira, there also. Renato Felber, where are you? Here. And I guess, and me. Okay. So again, thank the scientific committee for preparing and selecting the scientific programs, the extra works you had, because we have several issues due to COVID pandemics and difficulties to support in science overall, not just in Brazil, but Brazil, the situation is amazingly difficult. And it was very hard for us to carry on this project. And well, in some sense, we consider that we are succeeding. Okay, so the restrooms. We have a restroom at the back part of the auditorium. We shall use also restrooms in the building on the left and also behind you. Okay, we're gonna have some coffee breaks, so we're gonna show you the place properly at the time of the coffee break. Okay, probably you're gonna have a picture on Wednesday. And so what else? So a few words about our graduate program. So our program is open to collaboration, and we have good students. So soon enough, I believe that you're gonna see some of them working or studying with you. So we are open for this kind of collaborations. So we don't have a PhD program yet, but we're working on this subject. We'd like to thank the sponsors. So the NCT Math, Professor Jacob Palles and Professor Lorenzo Dias. It was fundamental for the realization of this event. And here at UF is Professor Atereldis is good, gave a good part of the financial support for us. We don't really know if you're gonna use it because there are not much people here, but we understand the situation, and people had difficult to find financial support to come, and the situation is not easy. But anyway, we saw the quality of the book of abstracts. We're gonna thank a lot all the people that submit the works because they are of very high level. Thank you. And thank you for coming, those of you who are here. Well, the idea of for young people, I guess we need some few words. You are really invited to participate, to ask, to talk to people after the talks, their talks, to talk about their works and your works, and try to develop more science. This is one of the main ideas, something that you are bounded to do. Okay, so the main idea of the joint events is to generate science in between differential equations, dynamical systems, foliation theory, singularity theory, and this is starting to work very well here for us. And I hope you can find a way to collaborate with each other and to find nice problems and to find good students to work with. So I guess it's time to give some space, some room to Jelonek to prepare his talk. And so, oh yeah, I forgot to mention Professor Valdemar and Professor Yuri that gave some financial support for us, also for NUFIS. They were very important to ensure that we're going to realize this. So it's time to quit now, and we resume in 10 minutes again, I believe. Last thing is at 9 a.m. Okay? See you. Thank you.
Carolina, tem alguém daí do comitê? Só uma sugestão, pedir para mandar o
Oi,
link
tô
da
aqui.
programação. Teria como mandar o link da programação aqui no chat para gente, por gentileza? Só para ficar mais fácil. O Pepe acho que acabou de chegar. Olá, Pepe.
Eu vou pegar.
Posso mandar aqui? Eu posso mandar.
Eu acho que o Thiago tem esses dados melhor. Se o Thiago
Eu mando
puder.
aqui agora, só um minutinho.
Tá bom.
Perfeito. Acho que o Pepe chegou aí. Hello, Pepe. Good
Obrigada.
Hi, Pep. Pep, I think your audio is turned off.
Microphone is turned off.
You should turn on your microphone. Pep. Oh, well.
Good morning, everybody.
Good morning.
Morning. Oh, sorry. we have time. Raimundo, it's okay with my slides?
I
No,
cannot see your screen yet.
Ah,
I think you.
No.
I think
there is?
you have to share the screen first.
Okay, okay, but it is. Now it's okay?
No,
Wait
yet.
okay, it's loading. Wait a minute.
Okay.
Now it's perfect.
Yes, good.
Okay, thank you.
So it's my pleasure to introduce Professor Zbigniew Jelonek from IMPAN, Poland, and the title of his talk is On the Extension of bi-Lipschitz Embedding. Jelonek, please.
Thank you. Thank you very much for invitation and giving me this possibility to have this lecture. No, maybe that's a pity that not in person, because I know that surroundings in Brazil is beautiful, especially in this place. No, but anyway, it's my pleasure to have this lecture. And I would like to present my work with Birbrar and Fernandez. It's about the extension of bi-Lipschitz mappings or embedding, as you mentioned, okay? In modern Lipschitz geometry of singularities, there are two natural metric and three natural classification problems. A semi-algebraic or algebraic subset can be equipped with inner metric, or in other words, the length metric, defined as minimal length of path connecting two points, or with outer metric, simply the metric which is induced from the ambient space. One can define by Lipschitz inner equivalence, Lipschitz outer equivalence, and Lipschitz ambient equivalence. Yes, this means that two sets are called Lipschitz inner equivalent if there exists a bi-Lipschitz map between the two sets with respect to the inner metric. Of course, everybody know what it means by Lipschitz. Yes, that simply the metric is controlled up to some constant. Yes. Okay, maybe I by Lipschitz mapping, you know. Okay, maybe you see the paint.
Yes.
Yes.
Okay, simply yes. The mapping is by Lipschitz if satisfy this. Maybe in the norm, because we are in the Euclidean space. Yes. Okay, this means that it is maybe not is isometry, but it is close to be isometry. Okay, now I have to. Okay, I am okay. The sets are called Lipschitz outer equivalent if there exists a bi-Lipschitz map with respect to the outer metric. This means this simply the metric of Euclidean space. Okay? Finally, the sets are called ambient Lipschitz equivalent if there exists a bi-Lipschitz map with respect to the outer metric that can be extended as a bi-Lipschitz map to the ambient space. This means simply that these sets are these two sets are lie in the same way with respect to the metric in the ambient space. Yes, this is important observation. Okay. the relation between the inner and outer matrix are very well investigated, and the theory of Lipschitz normal embedding is on the rapid development. There are, say, for example, there is many works, for example, Misev and Pichon and Kerner, Pedersen and Roaz. Our work is devoted to the relation between the outer equivalence and the ambient equivalence relation. Simply, we would like to show that under some natural assumptions, if the two semi-algebraic sets are outer equivalent, that they are automatically ambient bi-Lipschitz equivalent. This is a new result. A recent work of Neumann and Pichon showed that even in the case of germs of complex surfaces, the outer Lipschitz equivalence does not imply the ambient topological equivalence. This means that this natural assumption simply is that there is no topological obstruction. Yes. In particular, the dimension is relatively large, not very large, but relatively large. One of the very basic examples in the paper showed that two compact curves in the plane can be outer Lipschitz equivalent, ambient topologically equivalent, but not ambient Lipschitz equivalent. And I would like to give this example. Mainly we have, okay, and we have here two cusps, yes, but these cusps are different, yes. Simpler, this means that here the order of contact is different here and here, yes, and then take this, but which looks like this. Here is blue and the red is here. Okay, then you see these two objects are outer equivalent, outer bi-Lipschitz equivalent, because it's easy to construct bi-Lipschitz mapping. Moreover, they are ambient bi-Lipschitz equivalent because you know it's easy to extend this homomorphism to the whole, because homomorphism does not distinguish order of contact. However, if you use Jordan theorem, then you see that any bi-Lipschitz homomorphism which preserves order of constants cannot change this cusp which is inside the circle to this side which is outside the circle. Yes? That this, hence, if we have a bi-Lipschitz mapping, this means that this cusp blue can be transformed on the red. This is impossible. Yes? That we cannot construct global bi-Lipschitz mapping from R2 to R2, which sends this curve, this semi-algebraic curve onto the second one. Yes, it means that we need some assumption to do this. Yes, okay. On the other hand, the example of Bilbray and Gabrielov showed that for germs of real surfaces, the outer Lipschitz equivalents, considered together with ambient topological equivalence, don't imply ambient Lipschitz equivalence. It is a very similar situation as on the previous picture. Given a semi-algebraic set X of dimension K, how one can estimate in terms of K the dimension of the space Rm such that there exists a bi-Lipschitz embedding of X into Rm? And we prove this very nice theorem. It is a Whitney type theorem, yes, for bi-Lipschitz category. Let X be a closed semi-algebraic set of dimension K with the induced metric. Then there exists a bi-Lipschitz and semi-algebraic embedding of X into R2K plus 1. Moreover, if F is an algebraic variety, then we can assume that Fx is also an algebraic variety. This means that, in fact, all chi-dimensional semi-algebraic sets with respect to the metric are embedded in relatively small space, R2K plus 1. Okay. We give also a complex version of this result. Any compact semi-algebraic set X of dimension. Another result of this type is any compact semi-algebraic set X of dimension K is bi-Lipschitz equivalent with respect to inner metric to a Lipschitz normally embedded semi-algebraic set, which is embedded in 2K plus 1. This is a generalization of Mostowski-Birkbara result. Well, we simply use to Mostowski-Birkbara results our theorem, and we obtain this. This means simply that, again, we have relatively small space at which X is embedded. When the outer Lipschitz equivalence implies the ambient Lipschitz equivalence. In general, 2 bi-Lipschitz embedded into R2K plus 1 are not ambient equivalent. This means that the embedding is not unique. We say that the semi-algebraic set X admits a unique embeddings into Rn if for any 2 bi-Lipschitz embedding f, g, x to Rn, where fx, jx are semi-algebraic sets, there is a bi-Lipschitz homomorphism such that G is simply the composition of this bi-Lipschitz homomorphism of Rn with F. This means that they are embedded in the same way. In other words, X has a unique embedding into Rn if any other semi-algebraic subset, which is equivalent to X with respect to the outer metric, is ambient Lipschitz equivalent to X. Using theorem 3.3, this was one. Oh, this was this Whitney type theorem. We can modify the algebraic methods developed in my old paper, the paper of Kaliman Srinivas, to the Lipschitz category, and we obtain the following result. That maybe let me recall the definition before I state this result. We say that a Lipschitz homomorphism is tame if it's of this form. Yes, here you have the same variables, and on the last variable is xn plus p x1 xn minus 1. This p depends only on the first tuple of these variables, and p is Lipschitz method. Then you see that note that such a mapping has almost everywhere Jacobian equal to 1, hence it preserves the n-dimensional volume of Rn. In fact, all our extensions are of this type, that they preserves the n-dimensional volume of Rn. They are bi-Lipschitz and they have this extra property. Okay, I'm sorry. And now we have this our main result. I try to later explain some details of the proof, not many, but some of them. Yeah? But first I formulate this theorem. Let X be a closed semi-algebraic subset of Rn of dimension k. Let F be a semi-algebraic and bi-Lipschitz embedding. If n is greater or equal to 2k plus 2, then there exists a tame bi-Lipschitz and semi-algebraic homomorphism such that which is the extension of F small. Moreover, there is a continuous semi-algebraic family of tame bi-Lipschitz semi-algebraic homomorphisms such that we have F0 is identity, Fn1, F1 restricted to X is our F small. Now, this theorem is simply a counterpart of well-known theorem from topology about isotopy of two embeddings of smooth varieties into Rn. Yes, it is exactly the counterpart. This is, in some sense, we discover some similarity between the category of smooth manifolds in Rn and the category of bi-Lipschitz mapping of Rn with when the objects are semi-algebraic sets. That if you replace smooth variety by semi-algebraic variety and category of smooth morphism to the category of smooth bi-Lipschitz mapping, the results are more or less the same. This is very interesting. Okay. In particular, we have the following corollary. Let X be a closed semi-algebraic set of dimension k. If n is greater than 2k plus 2 or equal to 2, then X has a unique semi-algebraic embedding into Rn. This means that we can embed it, such an X only on one way to Rn with respect to the metric. Yes. Using slightly more subtle method in the local case, we can obtain some better local results. In fact, we have the following theorem: let X0 be a germ of closed semi-algebraic set of dimension k. You hear me, yes? Raimundo?
Yes, we can hear you. Yes.
Okay. Because I may be offline. Okay. Let X0 be a germ of closed semi-algebraic sets of dimension k. Then there is a bi-Lipschitz semi-algebraic embedding of X0 into R2K0. Yes, this means that, for example, every curve can be embedded into R2, but it is for curves, this result was first discovered by Tessier. Yes, no, but our result is general, and also we have also a complex version of our theorem that X0 be a germ of closed complex algebraic affine variety of dimension k. Then there is a bi-Lipschitz and regular embedding of X0 to C2k plus C2k, such that Fx is a germ of complex algebraic variety. Okay, and this theorem generalizes a result of Tessier. Yes, in fact, Tessier proved this theorem, but only for k equal 1, and his method was much more complicated because he uses this theory of this his modules. Okay. And we have also the analog of theorem about extension of embeddings in the local case. Yes, that if X0 be a germ of a closed semi-algebraic subset of dimension Rn0 of dimension k, let Fx0 Rn0 be a semi-algebraic and bi-Lipschitz embedding. If n is greater or equal to 2k plus 1, then there exists a germ of a Tame bi-Lipschitz and semi-algebraic homomorphism, such that again it extends F. That's locally we can drop a dimension by 1. Yes, these results are better. Moreover, there exists it's the same. There exists a continuous semi-algebraic family of germs of Tame bi-Lipschitz of Tame bi-Lipschitz mappings. I'm sorry to hear you. And there exists a semi-algebraic homomorphism such that F0 is identity, Fn1x is F. It's the same theorem, but we can decrease its dimension by 1. Now, in particular, let X0 be a germ of closed semi-algebraic set in dimension 2k plus 1, then X has unique embeddings. This means that such a germ can be embedded in R2k plus 1 only in one way. And finally, we prove that by a slightly different method that if X0 be germs of one-dimensional semi-algebraic subset of R2, and they are outer bi-Lipschitz equivalent and they are ambient bi-Lipschitz equivalent. However, here we don't assume that it is the extension of this embedding. There exists simply such a mapping with respect to these sets. Okay. And you know that our results are sharp because, in fact, there are germ of surfaces in x0 and y0 in Rn, and a semi-algebraic bi-Lipschitz mapping which can be extended to homomorphisms of Rn0, but it cannot be extended to a bi-Lipschitz homomorphism of Rn0. Such exams was constructed by Birbar and Gabrielov. This means that our result is the best possible, yes, because our result works for n equal 5, yes, but you see for n equal 3 and n equal 4, it cannot be applied. Okay, now I would like to see to say a few words about proofs of this result. In fact, in our paper, we try to use algebraic method, yes, simply to reduce semi-algebraic geometry to, in some sense, to algebraic geometry. Now, of course, it is, but we try to use these methods, yes, to simplify all, because you know, by Lipschitz geometry is, you can imagine that you can estimate it some norms and so on, and then all subjects is very complicated. But the solution, the good solution here is to see bi-Lipschitz mapping as a geometric object, not metric object, but geometric object. Yes? And we will try to do this exactly, to simply to build geometry. A part of this geometry is our bi-Lipschitz mappings. Yes? And then we can use geometric methods to solve our problems. Okay, then we consider the Lipschitz category L. Its objects are closed subsets of Rn, in our cases semi-algebraic, equipped with the outer metric, and morphisms are Lipschitz mapping with respect to the outer metric. We also consider the Lipschitz semi-algebraic category Ls. Objects are closed semi-algebraic subsets of Rn, equipped with outer metric, and morphisms are Lipschitz and semi-algebraic mappings. In fact, we mainly use this second category. Yes. We start with the following basic definition, which is valid in both categories. Yes, let X be a closed semi-algebraic subset of Rn, and Fx and X from X to Rn be a Lipschitz mapping. We say that F is a bi-Lipschitz embedding if the mapping Fxy is a bi-Lipschitz isomorphism, and F and F2 minus 1 are Lipschitz semi-algebraic mappings. Here it should be Lipschitz, yes, but okay. Note that bi-Lipschitz embedding is a closed mapping. In particular, we have Fx is equal to y. It's closed, and the mapping Fxy is a homomorphism. No, it is. It follows from the Cauchy theorem and the theorem of invariance of domain. Yes, that all our mappings in fact satisfy these results, yes, which we use here. These extensions, that the image of Rn is Rn. Okay, and now we try to build the analog of coordinate ring, okay, in algebraic geometry. Let X be a closed subset of Rn. We will denote by Vx the vector space of all Lipschitz function on X. If Fxy is a Lipschitz mapping of closed sets, then we define the natural morphism. Yes, from contravariant from Vy to Vx. It's simply the composition. It's well defined, and here is similar. In closed semi-algebraic category, we additionally assume that this mapping is also semi-algebraic, not only Lipschitz, but Lipschitz and semi-algebraic. Okay. Since every Lipschitz function on X is the restriction of some Lipschitz function on Rn, we have that the mapping is an epimorphism. And in fact, the only theorem which we use here from the only information that the mapping is Lipschitz, which we use here, is this It is it is well-known theorem that every Lipschitz mapping can be extended from closed subset to the ambient space. Yes. In fact, we need only this information, and we use some geometric methods. That the key point is here. Yes. That if the mapping that this mapping is epimorphism. Yes, this means simply that every Lipschitz mapping can be extended to a Lipschitz mapping. Yes? This is old and well-known results. Yes, and now we have to transform the notion of bi-Lipschitz embedding to some algebraic condition. Namely, the following two conditions are equivalent. F is a bi-Lipschitz embedding. The induced mapping V from Rn to Vx is an epimorphism. This is the fundamental result, and it follows from this simple observation. Not a simple. This is, of course, this is interesting. It is a very interesting theorem with simple proofs. Yes, that every bi-Lipschitz mapping can be extended to the ambient space. Yes. Because simple does not mean trivial. Yes? This result is extremely interesting. No, but nowadays well known, yes, and it has simple proof. But the same result holds in this LS category. Yes. In fact, we deal mainly with this category. Yes, that F is bi-Lipschitz semi-algebraic embedding. This means that this induced mapping is an epimorphism. Okay, and now we have lemma, and that let X be a closed subset of Rn. Assume that the projection is a bi-Lipschitz embedding. Then there exists a Tame bi-Lipschitz homomorphism which extends this. And maybe I give a proof of this in some short way, because to have a flavor of this paper. Yes. Okay. So I have to change how to do this. Maybe use simply this. No. Probably I can change the paper. How to change this? I don't know. Oh, maybe this. Oh, maybe I do it this way. Okay, I'm sorry. And now we have the following situation. Here is this pen. Okay, we have here. Oh, maybe color. We have here X. Yes. We have here X. We have here these coordinates. Here you have variables X. Here we have variables Y. And we know that this projection is epimorphism. This projection is bi-Lipschitz embedding. Yes, but this means that the mapping from V R X R Y to Vx. I'm sorry, here is from Ry, because it's embedding here. Yes. Is epi, that this mapping is epimorphism. This means in particular that for every xe, there exists a function bi-Lipschitz function of this form. Oh, that xi is equal to pi y. Yes, every variable here is equal to some function of variables here. And now, if we take the mapping x1 minus p1 and xk minus pk, and here we get y, then you see that this mapping is bi-Lipschitz. It's easy to see because it's triangular. All these are Lipschitz. Yes, and on x this function vanishes. Yes, because xi is py y, that this function vanishes. And in fact, you see that this mapping phi restricted to x is simply this projection. Yes, because it sends x y to 0 y. It's exactly as this projection. That we use simple algebraic tricks to do this. Yes. Okay, we have this theorem. And now I also sketch the proof of the Whitney embedding theorem because it's interesting and it's relatively simple. Yes, if you see on this direction, namely the proof is the following. Again, the same trick. Probably is better solution, but I don't know it. Okay, how to prove that some semi-algebraic sets can be embedded into R2k plus 1. Yes, R2k plus 1. And we use the original, in some sense, original idea of Whitney, namely we consider the set of all seconds here. Yes, okay. And this set of seconds, since x is semi-algebraic, that this set of seconds has dimension 2k plus 1. Yes, and we consider this lambda is the set of seconds. Yes. Yes, and we consider, in fact, not this set, but only the direction of these seconds at infinity. And this is 2k dimensional subset. Yes, simply we take this second and we choose a point on the hyperplane at infinity, which these seconds give. Yes. And we take a closure of all these points at infinity and denote this by lambda, maybe in this way. Yes. And now you see we have when n is greater than 2k plus 2, that or equal, that we can choose here a point at infinity which omits all the direction of all of these seconds. Okay. In fact, we can choose. Okay, and now choose this point. Here it gives direction of some lines. Choose a hyperplane which is orthogonal to this line. Okay, and consider this orthogonal projection. I claim that this orthogonal projection is good. It gives a bi-Lipschitz embedding. How to prove this? This is very easy. Yes, but I have to enough again. The space. Again, I use this trick. Okay. Because why? Why? You see, here you have one. This is here. Here you have 1 point. Here you have another point. Here you have this second, and here you have this projection. Yes, this line gives this projection. Yes, they are parallel. And here you have the 90 degrees, the angle 19 degrees, and here you have x, y, and here you have y prime, x prime. Yes, this means that this is d, and this is the distance between the images. Yes, but if you take here the angle alpha, you see that d prime is simply d sinus alpha. Yes. On the other ways, x minus y prime is x minus y sinus alpha. However, note that the angle between the line L and this maybe will be the center. The projection is given by line L. Yes, that it is non-zero for every L which belongs to our set lambda bar. All this direction of seconds at infinity. Yes, by the assumption we choose this line L in this way. Yes. No, however, the projective space is compact, and this angle is a continuous function. Yes, this means that it has minimum. That this angle has minimum on all these sets. The sinus alpha has a minimum. Okay, because sinus alpha is non-zero, and it has minimum. Yes. But if this minimum we denote by epsilon, this means that x minus y is x minus y is greater or equal x minus y epsilon. Of course, is greater because projection is a linear function. We have this. Both these two conditions implies that the mapping is bi-Lipschitz. Okay, I have no time. Okay, I see. Okay, that of course we have this Whitney lemma which I mentioned before. Yes, that every closed semi-algebraic set can be embedded into R2K plus 1. This result is sharp because in general you cannot embed a semi-algebraic curve in a bi-Lipschitz way, even if there is no topological abstraction to do it. And we have nice example of Sampaio which illustrate this, but maybe I skip this because I'm afraid that I have not so much time. And again, maybe I recall the proof of this Birber-Mostowski result, which I mentioned. Yes, that any compact semi-algebraic set of dimension k is bi-Lipschitz equivalent with respect to the inner metric to a Lipschitz normally embedded semi-algebraic set in R2K plus 1. And the proof is the following. By Birber-Mostowski theorem, there exists n, maybe big, such that x is bi-Lipschitz equivalent with respect to the inner metric to a Lipschitz normally embedded semi-algebraic set y into Rn. And using our lemma of the Whitney type, there is a bi-Lipschitz homomorphism phi Rn to Rn such that this y is embedded in R2K plus y cross 0. But phi preserves the equivalence of the inner metric and the outer metric. That in fact we can take as y is imaged by phi, which is embedded in R2K plus 1. Okay. Maybe I skip this. Okay. Okay, that's in fact, in general, if we have a linear projection, that in fact, from the projective point of view, it means that following: here you have hyperplane at infinity. Here you have the center of the projection, which is the linear subspace, and simply you have here this space over which you project. This means simply that you take a space which is spanned by this center of the projection C, by this point, and you take an intersection point of this object, of this linear space with this linear space. Yes. In fact, every projection Rn to each H looks like this. Yes. I need this for what is this? For other. That we have a generalization of our earlier observation, the observation which I did when I tried to prove this Whitney theorem. Namely, you have more general result. Let X be a closed subset of Rn, denote by lambda a set of all direction of X, and denote sigma closure of lambda. Then the projection Rn, let PL be a projection with the center L. Then restriction of this projection to X is a bi-Lipschitz embedding if and only if the center is disjoint from sigma. The center of the projection is disjoint from the closure of direction of all seconds to X. This is very important. And we have, maybe I skip this because it's and now we have the result, the lemma. Maybe I'm sorry. We can go to the proof of this classical result using. I'm sorry. How many time I have? Raimundo.
Hello, Jelonek. So
How many time?
Tiago, are you?
Yeah, I think you have 1 minute, Professor Jelonek.
1 minute.
Okay, good.
Okay, that's using similar methods we can do the rest more or less. I believe that I was in a position to show the spirit of this paper. Using such a geometry trick, we can also obtain all this the rest of results. In fact, by this method, we reduce our study to some methods from algebraic geometry. And then maybe I stop in this moment.
How many minutes for questions, Tiago?
I think we have 5 minutes per question.
5 minutes? Okay,
Yes.
okay. Professor Jelonek, go ahead. If you want to show your proof, do you have still 5 minutes? I am asking for that.
Okay, thank you.
Okay, go ahead.
Okay, that's in fact the proof of this Main theorem is depends. Oh, I'm sorry. Where it was. Oh, in fact, we have this lemma, which is crucial here. That if X is a closed semi-algebraic set of dimension k and n is greater or equal to k plus 1, we assume that the mapping from X to Rn and to the one copy of Rn, because we have here Rn cross Rn, yes, to the first copy of Rn and to the second copy of Rn are bi-Lipschitz embedding, then we can change the variables in the first copy of Rn and in the second copy of Rn in this way that all mappings of this type where here are exactly n variables. The first r variables are from the first copy, and the rest variables is from another copy of Rn. That all these mappings are embeddings. Okay, and now if you know this, you can prove, you can obtain the proof of this theorem in the following way. Maybe this is important that I, okay, that we start simply from the mapping Z1, Zn minus 1, 0, because we can embed it, our set in the space Rn minus 1 cross 0, yes. And now you see, we can use the mapping of the type Z1, Zn minus 1, Zn plus P, Z1, Zn minus 1, in this way that this P is Fn. Okay? In fact, we have the mapping now Z1, Zn minus 1, Fn. However, all these variables up to this and these variables generate the vector space of Lipschitz function. In fact, we can kill these variables by Zn minus 1 is equal to Q1 of Z1 Zn minus 2 Fn. Yes, we use only these variables and this one. And now we can kill these variables using the morphism Z1 Zn minus 2. Here it is Zn minus 1 minus Q1. And here is this Fn. Now we obtain here 0, and we can repeat this situation up to we obtain
good.
0 F2 Fn. It is simply algebraic transformations. Not more here we do. This is simply, and using this operation, we from this mapping we obtain this mapping. This means that these two mappings are bi-Lipschitz equivalent. Yes, this mapping is but identity embedding, and this is our embedding. This is more or less the method.
Okay, good, nice. Very nice.
I'm sorry that I had no, because maybe I spent too much time for this explanation. Yes. Okay, there are some.
No, that's fine. Good. Tia, go ahead, please. Sorry.
Thank you, Professor Jelonek.
Have you finished your talk? Jelonek.
Yes, I think.
So let's thank the speaker, please.
Thank you very much.
So now we're going to proceed in this way. I guess it's going to be better. I'll ask the audience here if there are any questions and comments. Then I go online, okay? So are there questions or comments here? So Miriam has. Wait a minute, please. I'm going.
Thank you very much. I was just curious if you have two semi-algebraic subsets of Rn. So is there any condition for them to be ambient equivalent if they have they obviously if they have same dimension?
No, yes, it's enough that they are bi-Lipschitz equivalent, and the dimension is not greater or equal to 2k plus 2. Yes.
If the dimension of these subsets, or
if the dimension is k and they are bi-Lipschitz equivalent, and they are embedded in the ambient space has dimension greater or equal to k plus 2, then they are automatically ambient equivalent.
okay, right.
Any other question or comment? No? So now we ask people online if there are questions or comments. No one? So let us thank the speaker again, please. So we resume at 11 a.m., please. So let us verify the technical details for the next speaker. Go ahead, Thiago. Please help him.
I think what's happening? I didn't understand.
To help Rafał, if is everything okay for him to start to speak at 11. 11, no, excuse me, 10 to 11 a.m. 9:50. 3
I
minutes.
think, the next, let me see here. No, it's 95.
10 to 11. 9:50.
Yes.
That's the program, isn't it? Is he okay? Rafał?
Yes, and do you see the PDF file?
Yeah, you just to check if it's everything okay.
So you see it. Okay.
So let us wait 2 more minutes, okay?
Okay, thank you. Thank you very much.
So, can you hear me? Okay, thank you. So now we're gonna have Professor Rafał Pierzchała from Jagilellonian University. I hope I'm speaking properly. And his
Jagilellonian University. Yes,
okay, thank you for enlightening us. Then the title of his talk is Tame Geometry and Polynomial Inequalities. Please, Rafał.
Thank you very much. Thank you for giving me this opportunity to give a talk during this nice conference. I will talk about polynomial inequalities in the context of semi-algebraic, subanalytic, and more generally, minimal geometry, and in the context of singularity theory also. The aim of this talk is to provide answers to some problems concerning polynomial inequalities. And these problems are the following. Given a map H in a certain quasi-analytic Donjois-Carleman class, we will show how to decide whether the image under H of a set satisfying Markov inequality or Nikolsky inequality satisfies Markov inequality, respectively, Nikolsky inequality. These two questions have been open until now, even for H being analytic. The second problem I want to address is to establish the relation between Markov inequality and Nikolsky inequality, both in general setting and in and the last problem I'm going to discuss is to show that each compact definable in a non-minimal structure set satisfying Markov inequality must be fat, that is or its interior. This solves in the minimal category the well-known problem of non-pluripolarity of sets satisfying Markov inequality. However, beyond the minimal category, the problem is still open. So these are the aims of the talks. And let me now give you some notation for a set E in Rn by modulus of E we will denote its Lebesgue outer measure. In fact, the only measure we consider this talk is the Lebesgue one. So we will write measurable instead of Lebesgue measurable. Moreover, for functions, we will consider the standard supremum norms, subnorm, but also the classical Lebesgue norms, namely for each measurable function H on the set E in Rn and each Q greater or equal 1, we define the standard norm, which is normally called LP norm, but P, I will denote by P the polynomials in this talk, so I just say Q instead of P. Of course, if Q is equal to infinity, this is the standard supremum norm. So let me, at the beginning, recall what are the classical polynomial inequalities in one variable. They come from approximation theory, and the most important of them are the following. The first inequality due to Andrei Markov, if P is a polynomial of one variable of degree at most n, then the norm of the derivative of this polynomial on the unit interval is bounded above by n square times the norm of the polynomial itself on this unit interval. This is the first inequality. The second inequality is due to Nikolsky. Nikolsky inequality compares two different Q prime and Q norm of the polynomial on the unit interval. More precisely, there exists a positive constant C such that for each polynomial P, one variable of degree at most n, and each q prime such that 1 is less equal q, less equal q prime, less equal plus infinity, the q prime norm of the polynomial on the unit interval is bounded above by this constant you see on the slide, c n to the power 2, 1 over q minus 1 over q prime, times the q norm of the polynomial p. And the last inequality I want to discuss is the inequality of Remes, namely for each subset of the unit interval of the positive measure, you have the following estimate. For each polynomial p of one variable of degree at most n, the norm of the polynomial on the whole interval is bounded above by some constant. You see here precisely on the slide, times the norm of the polynomial on the subset S. Here the Tn denotes the classical Chebyshev polynomial of degree n. In particular, you obtain the following estimate, simpler, not using Chebyshev polynomials, where lambda is just the measure of the set S over 2. Excuse me, do you hear me properly and see the
Yes, yes.
Yes,
Thank you. So what I want to talk about is to give the generalizations of these three inequalities to several variables. And this is where singularity theory and the geometry come in, because the generalization to convex sets of non-empty interior is rather easy of all these inequalities and well known. But the problem is, what about sets which are, for example, cusps in Rn, even very, very simple cusp on the plane? And the problem is not at all easy and not at all clear whether such inequalities are true or not true. And let me now discuss the first generalization, the generalization of the Markov inequality. Namely, we will say that the compact set in Rn satisfies Markov inequality, or is a Markov set, if there exists two positive constants kappa and c such that for each polynomial of n variables and of degree at most n, and each multi-index alpha, you can bound the norm of the derivative of order alpha of p on the set E by a constant Cn to the power kappa and to the power length of alpha times the constant times the norm of the polynomial itself on the set E. So it's important that this constant Cn to the power kappa grows not too fast with respect to the degree, namely it grows polynomially, not exponentially, but polynomially, and this is important from the point of view of possible applications. Of course, this inequality is enough to consider only for partial derivatives of order 1, because then you just use the induction, simple induction. And also you can define such inequality for compact subsets of R of Cn in the same way, but using, of course, complex polynomials. And let me give you some examples. But first, let me say that this inequality is of great importance in analysis. It was studied, for example, in connection with polynomial approximation of smooth functions, Sobolev type inequalities, Whitney's extension problems, this period of Whitney, Pfefferman, and others, pluricomplex green function. The people who studied such inequality are, for example, Baran, Borwein, Bos, Brudny, Derrick, Fredrik, Koncharov, Kroh, Levenberg, Milman, Pawłowski, Pleśniak, Siciak, Totik, and many others. Also, I didn't say that all polynomial inequalities I mentioned, they all come from approximation theory, and originally they were used in proofs of Bernstein type theorems, but nowadays polynomial inequalities have found a lot of important applications in areas which are well apart from approximation theory. For example, in convex geometry, in the theory of subelliptic differential equations, in number theory, in algebraic and analysis, in algebraic and analytic geometry, in complex analysis, in pluripotential theory, and several other branches of mathematics. Okay, so let me give you some examples of sets satisfying Markov inequality. The simplest example is a cube. Any cube in Rn satisfies Markov inequality. More precisely, for each polynomial p of n variables of degree at most n, and each multi-index alpha, you have the following inequality. And as you can guess, this is a simple generalization of the inequality of Markov for one variable just by induction. So Markov proved it for the interval, and generalization for cubes is a simple matter. The next example is not non-trivial, namely each non-empty compact set, that is the set which is the closure of its interior, and subanalytic in Rn satisfies Markov inequality. This is the Pawłowski-Pleśniak result. Let me recall what are subanalytic sets. Subanalytic sets is a generalization of semi-algebraic sets. Semi-algebraic sets were discussed in the previous talk. Let me say that those subanalytic sets are also generalization of semi-analytic sets, and semi-analytic sets are more or less the sets which are locally described by analytic equalities and inequalities. Also, some other natural families of sets satisfying Markov inequality are provided in some hominimal structures. But let me stress that all these examples belong to a larger class of so-called SPP sets, and also SPP sets satisfy Markov's inequality. And let me give yet another example, which seems very easy, but is not in the proof. Assume that you have E1 up to EM compact and pairwise disjoint sets such that the union satisfies Markov inequality, and one can prove, but the proof is not easy, that for EJ, the set EJ also satisfies a Markov inequality. So the results seems to be easy, but as I said, the proof is far from being obvious. The proof was given by Bos and Milman in a very a long paper and very deep paper in GAFA. Okay. To state some of my results, I also need some other terminology, namely, I will use the Donjois-Kaleman classes. Suppose we are given a sequence of positive numbers and let U be an open subset of Rn. Then by dm of U, I will denote the set of C infinity functions on U such that for each compact set K in U, there exists a constant gamma such that each derivative of order P has its norm on K bounded above by gamma to the power P plus 1 times MP. So derivatives are in some sense controlled by this sequence MP. And this set of functions is called Donjois-Kaleman class, or sometimes ultra differentiable class. They are important, for example, in differential equations. Also, I will consider Donjois-Kaleman maps, and they will be denoted by DMU Rn primes prime. The example, let S be a fixed real number. If MP is P factorial to the power S, then dm of U is just the class of Gevrey functions of order S in U. And if S is equal to 1, so the sequence MP is just P factorial, then the set dm of U is just the ring of real analytic functions. I will also use the following definition. A sequence of positive numbers is called admissible if M0 is less equal M1, and the following three conditions are satisfied. First of all, M is strongly long convex. That is the following inequality holds. This is the generalization of logarithmic convexity where you don't have this P factorial. The second condition we require is that M is quasi-analytic in the sense of Donjois-Kaleman class. In the sense of Donjois-Kaleman, that is the following sequence MP over MP plus 1 is divergent. And last condition, you have some control on the sequence MP, namely MP is bounded above by theta P to the power P over omega for all P. So any sequence satisfying these three conditions will be called admissible sequence. The simplest example is, of course, P factorial, and then you obtain analytic functions, as I said before. And also for a C1 map on an open set in Rn, I will use the following notation. U star is the set. This is simple. This is simply the union of those connected components of U, which meet the set of points where the rank of H is equal to n prime. That is maximal. And the main result of this talk is the following. Assume that H is from Donjois-Kaleman class, dm, such that M is admissible. And suppose that E is a subset of U, which is compact and satisfies Markov inequality. Then the following two statements are equivalent. H of E satisfies Markov inequality, and H of E is equal to H of E intersected with U star. So this result gives you possibility recognize whether the image of a Markov set is a Markov set. Then what you have to check is a simple geometric condition. The second in the last line, h of E must be equal to h of E intersected with U star. If, for example, the map H is non-degenerate, that is, at each component there is a point of maximal rank, then U star is equal to U, and the second condition is trivial because it says that h of E is equal to h of E. So then, if H is a don't-generate map from this class, then the image of any set satisfying Markov inequality also satisfies Markov inequality. Note that this image, of course, this is maybe a very complicated set. Even if E is simple, cube, for example, or ball, the image must be a complicated set having cusps and so on. So the problem is the singularities of the image, how to deal with them, how to prove that this image satisfies Markov inequality. And let me also say that, of course, in the simplest case where MP is equal to P factorial, we get the answer to the following problem, namely assume that H is a real analytic map and E is a compact set in U satisfying Markov inequality. And the question is, under what conditions does it happen that the image satisfies Markov inequality? If we apply the main result to the sequence P factorial, then we get the answer. The answer is very simple. Assume that H is real analytic, E is a compact subset of U with Markov property, then the following two statements are equivalent. The image satisfies Markov inequality, even only if the image is equal to the image of E intersected of U star. Okay. Theorem 8 is, in fact, quite strong because with no extra effort, we can recover from simplest form non-trivial results which I have already mentioned. And at first glance have nothing to do with theorem 8. For example, suppose that H is an open neighborhood of the unit cube in Rn. And suppose that this H is non-degenerate real analytic map. That is the set of points where rank is maximal is a dense subset of U. Then by the example 2 and by the main result, the image of this cube satisfies Markov inequality. However, it follows from the rectilinearization theorem due to Hironaka or Birston-Millman that each non-empty compact fed and subanalytic set in Rn prime is a finite union of sets of this form, where H is as above. So in this way, we can recover the Pawłowski-Pleśniak result that each non-empty compact fed and subanalytic set satisfies Markov inequality. This is the first example. The second example is the following. We can recover the Bos-Millman result, namely assume that E1 up to EM are compact and pairwise disjoint sets such that the union satisfies Markov inequality. And as I mentioned in example 4, for each J, the set EJ then satisfies Markov inequality, but this result is far from being obvious. Now I will show you how this example can be recovered from the main result of the stock, namely to do this, fix J and pick some point A in EJ. then take open sets U1, U2 in Rn such that Ej is contained in U1 and E minus Ej is contained in U2, and these two open sets are disjoint. And we defined a very simple analytic map, H of on the union of these two open sets, namely H of x is equal to x on U1 and H of x is constant and equal to A on U2. Then it follows immediately from the main result that the image is equal, satisfies Markov inequality, and this image is just Ej. So in this way, we've recovered the Bose-Millman result. As I said, to solve these problems, I need some techniques, some machinery from theory and for example, from ominimal geometry, which is a generalization of semi-algebraic geometry. Let me recall what ominimal structures are. An ominimal structure on the field R of real numbers is a sequence Hn of Boolean algebras of subsets of Rn, such that this sequence is stable under Cartesian products, contains all semi-algebraic sets. This follows from the condition 3. You see now this family is stable under taking projections, and the sets in H1 are exactly finite union of intervals and points. Let me recall that a set, if H is given, if an omnimal structure H is given, then we say that the set A is definable if it belongs to some Hn. And we say that the map is definable if its graph is definable. The simplest example is the omnimal structure of family of all semi-algebraic sets. Recall that the subset of Rn is semi-algebraic if it is a finite union of sets of the form you see on the slide. So these semi-algebraic sets are just the sets which are described by polynomial equalities and inequalities. We say that the nominimal structure is polynomially bounded if for each definable function f there exists L such that f of x grows at most like x to the power L at infinity. And of course, the omnimal structure of semi-algebraic sets is polynomially bounded, which follows from the Wyasiewicz inequality. And the key result used in the proof of the main theorem of this talk is the following. Result. Assume that H is a C1 map definable in a polynomially bounded nominimal structure, and assume that the set where the rank is equal to n prime is a dense subset of U. And we also need another assumption connected with polynomial approximation, namely suppose the following property holds: for each x in E is a compact set satisfying Markov inequality and containing U. For each x in E, there exists 3 constants and 4 constants, such that the ball center at x and the radius rho x is contained in U, and for each nu, we can choose a polynomial map hx nu from Rn into Rn prime, where the degree is of this polynomial map is bounded above by nu, and h minus hx nu on the ball, its norm is bounded above by the constant you see on the slide. And then the h of E satisfies Markov inequality. So this is one of the crucial results used in the proof of theorem 8. So this result, although theorem 8 seems to have nothing to do with minimal category, this crucial result, in fact, employs definable sets and definable maps, and also employs polynomial approximation. This is the second tool I use in the proof. So let me discuss the second problem of this talk, namely, it's well known that Markov sets in general can be very complicated. For example, they can be of measure 0, like Cantor-like sets. Therefore, one may ask about the topology of geometry of Markov sets, which are additionally definable in some minimal structure, for example, semi-algebraic or sub-analytic. And in particular, the following problem is quite natural and interesting, but the answer has not been clear up to now. The question is it true that definable Markov sets are fat? And the answer is yes, namely assume that the compact set E is definable in an ominimal structure. Of course, this can have some cusp and so on. If E satisfies Markov inequality, then E is fat. It is the closure of its interior. In fact, of course, one may ask about the converse of this result. And if an omnimal structure is not polynomially bounded, then the closure of the set. So this is the set defined by the infinitely flat smooth math. This set is compact, fat, and of course definable in any minimal structure which is not polynomially bounded by Miller theorem. But this set, one can easily show that this set does not satisfy its Markov inequality. And this is a simple calculation. But one can ask the following problem: what about polynomially bounded minimal structures? Is it true that all fat, definable, and compact sets satisfies Markov inequality? And this is a very hard problem, even for particular set like this. This is the set. This is the cusp. This is the cusp defined by irrational power R. And this is not clear whether this set, this particular set, which is of course definable in many minimal structures, it is not clear whether this set satisfies Markov inequality. This problem was studied about 20 years ago by Groen and Dradas, but didn't give the answer. Okay. However, in some minimal structures, there are some general results already mentioned in example 3, saying that all non-empty compact fat and definable sets satisfy Markov inequality. And these examples are given by Pawłowski, Pleśniak, and by myself. However, all these results are related to resolution of singularities in the spirit of Hironaka and Birston-Millman. And this resolution of singularities, of course, is in general is not available in arbitrary or minimal structure, even if this minimal structure is polynomially bounded. Let me recall also the following definition. A set A in Cn is said to be pluripolar if for each point A there exists an open neighborhood U such that A intersected with U is contained in the set where some plurits of harmonic function is equal to minus infinity. So this is the notion from pluripotential theorem. But let me only say that if a set in Rn is measurable and has positive measure, then this set is non-pluripolar. So we obtain via this lemma the answer to the following problem. Our Markov sets are non-pluripolar. We obtain the answer in the omnimal category. Because we, as I said, all such sets must be the closure of its interval. And excuse me, I have only 3 minutes. Is it okay? Excuse me. I
think you
Go
have
ahead.
3 minutes, Professor.
Okay, so let me finish this talk by discussing very briefly Nikolsky inequality, how it's related to Markov inequality. A generalization of classical Nikolsky inequality for any subset of Rn is the following. We say that the set E satisfies Markov inequality for polynomial P of degree at most n. You have this estimate. You have this comparison of Q prime norm and Q norm of P. And also another definition, we say that a measurable set in Rn is UPT if there exists sigma theta such that for each A in E and for each R, the intersection of E with the ball is greater or equal to theta R to the power sigma. And the second main result of this talk is the following. Let E be a compact set in Rn, then the following 3 statements are equivalent. S satisfies Markov inequality, E satisfies Nikolsky inequality, and E satisfies Markov inequality and E is UPT. So you have this assumption on the measure, this intersection of E with balls. And it is equivalent to Nikolsky inequality. In the last condition, equivalent to all this is the following. There exists 4 constants such that you can, in fact, you can compare the Q prime norm of any derivative of order alpha by the norm of the polynomial itself, the Q norm. And I also obtained the strongest version in polynomially bounded omnimal structures, namely the following 2 statements are equivalent. E satisfies Markov inequality and E satisfies each of the 3 equivalent conditions of theorem 22. So let me skip, and I have no time to discuss Remez inequality, but let me finish this talk by saying that a generalization of the Remez inequality in higher dimensions implies Nikolsky inequality, and this is equivalent to Markov inequality plus condition UPT. And in polynomially bounded omnimal structures, the Remez inequality implies Nikolsky inequality, and this is equivalent to Markov inequality. So thank you very much for your attention. Thank you.
Thank you, Rafał. I would like to ask you if you have any kind of questions or comments, but it seems that you have problems with the microphone. So, okay. Any questions or comments? So, people online, Are there questions or comments? So, okay. If not, well, it seems that there is someone asking, wanting to ask or not. Just open your microphone if you want to ask something and go ahead. Is there someone? Okay. It seems there is no question at all. So, okay. Thank you for your talk, Rafał. I would like
Thank you very much.
to ask you to thank you again.
Thank you very much.
So now we're gonna have a coffee break, and we're gonna resume at 11 a.m. So those that had not checked in, please check in now and well go to the coffee. We come back at 11 a.m. Thank you.
Ó, agora o microfone está funcionando. Na hora das perguntas não funciona. Está dando microfonia. Estou falando. Abaixa um pouco, mas não abaixa muito. Será que a galera lá escuta? O microfone está desligado, né? Então, tá. Agora está funcionando. Na hora que precisar, eu não sei o que vai acontecer. Na live do YouTube tá saindo. Oi. É. Sim. Esse daqui agora tá funcionando. A hora que
Fala um.